Okay, so we're going to be talking about the network layer. Now, we're already familiar with uh, models like the OSI model, TCP model, and amongst those, they both have a layer called network layer. And now, the responsibility of the network layer is host-to-host communication across various networks. So, let's say I have this example. I have two independent networks, and I have a router connecting them. Let's say I have a host in network one that wants to communicate to a host in network two. It is the responsibility of the network layer to ensure the packet is securely routed and reaches the host. But here we encounter our first problem. How do we identify our destination? How does the router know which host to forward the packet? And let's say the host has to return a packet. How will they know the source destination? So here we introduce the concept of IP addresses. IP addresses are logical addresses, uniquely and universally, that define the connection of a computer. So each host here will have an IP address that defines a connection to this line. So there are a bunch of versions of the IP protocol. Two main ones that we need to concern ourselves with are IPv4 version 4 and IPv6 version 6. IPv4 is only 32 bits now, and IPv6 is 128 bits now. And we'll see why this is important later on. Okay, so we'll start with IPv4. Each address, as we already learned, is a unique connection. Is a unique number that defines the connection globally. Now, what is address space? Address space is the total addresses available. So for 32 bits, total by 32, we have roughly 4.3 billion addresses available. In other words, if every system on Earth used IPv4, roughly 4.3 billion of them could connect to each other at once. Now, for IPv6, since the number is a lot larger, uh, the total number of systems is this number is incredibly large. Representation. Now, let's say I have an IPv4 number. How do I represent it? Now, while it's a 32-bit number, for human readability and usability, we represent it in chunks of 8 bits or 1 byte. That's separated by a dot. So 172 dot 192 dot 13 dot 0. Each of these correspond to these 8 bits, and they're all joined together by dot. So this corresponds to one IPv4 address. In terms of bits, if I had a stream of all these bits continuously, that would be the same as the IP address. Okay. So now let's see how exactly the addressing works. So first we have classful addressing. This introduces the concept of classes, which is now considered obsolete. So it's not used anymore, and we will see the reason why. But each class has been occupied some address space of the IPv4 class. And we have five classes, A, B, C, D, and E. Here D and E are special classes that we will not concern ourselves with too much. The main ones are A, B, and C. So how do we distribute IP addresses based on into the different classes? So this is how we do it. Based on the value of the starting byte. In other words, starting bits. So for the starting byte, if the value ranges from 0 to 127, it's a class A IP, 128 to 191 at class B, and so on for C, B, and E. And we can also write in another way. If the starting bit is 0, it's class A, starting bit is 10, and B. So for example, the IP address we have over here, it starts with a 10. In other words, it's a class B IP address. Now, of course, based on the nature of how we're assigning classes, the block size and the number of blocks in each class is going to be different. So we can see class A has the largest blocks, with just 128 numbers of blocks, and class B has smaller, more blocks, and so on. Each of these blocks has a fixed size that cannot be changed, and this is where we run into one of the issues. When we assign blocks, there's a lot of wastage. So let's say I have some organization and I assign them the class C, one block of class C. They have 256 IP addresses that they can use, but they only use 70. In other words, 180 IP addresses are wasted here. These IP addresses that will be shared to someone else. So to counter this limitation, we now use CIDR, classless interdomain routing. Now before we continue with CIDR, few important concepts on address depletion. Name is pretty self-explanatory. Running out of addresses in the address space. So comparing to the earlier example, if the organization was using 250, then they would be running out of IP addresses for any future hosts. Subnetting, dividing an address into contiguous groups, assigning each a smaller subnet. So we have one large net and you're breaking it down to smaller subnets. This gives you more networks. And supernetting, combining multiple blocks into one large net to increase number of hosts. So you're combining multiple networks to give you one large network. Now, we go on to classless addressing. So to overcome address depletion, for classless addressing, classes do not exist, but addresses are still assigned in blocks. And there are a few rules we have to follow while assigning these blocks. So for these address blocks, blocks must be contiguous, that is one after the another. So 18.1, 18.2, 18.3, they all must be consecutive in time, address space. The number of addresses must be a power of 2. So 2, 4, 8, 16, so on. And the first address must be evenly divisible by the number of addresses. So another thing we need to know is a mask. What is a mask? Mask is a 32-bit number where n leftmost digits are 1, rest are 0. And we'll see what it is in just a bit. And the purpose of this mask is to separate the IP address into network ID and the host ID. Network ID is used to determine what is the network. Host ID is which exact machine. So this is the CIDR notation. How classless classless IP address is written. X dot Y dot Z dot T. Here all of the X, Y, Z, and T, they are 8 bits, similar to what we saw earlier in class full address. And slash n is used to, this is a new thing we have, and this is used to determine the mask. So this is the n we saw earlier. Larger the n, the greater the mask. And using our IP address, we can find the first first address of each block. So set the rightmost n minus 32 minus n bits to 0, and that is the first address of any block. And vice versa, if you set them to 1, it's the last address of any address block. Now, few special addresses to note. First address of any address block is considered as a special address and used to refer the entire network. This is just one of the few special addresses. Other than this, also the last address of the network is also not used. Also, the address ending with .1 is used to broadcast bunch of links. Next, we come to network address translation. Uh, Network address translation is used to serve a large number of local IPs using just a few global IPs. So you can essentially provide recurrent connection to multiple hosts using very few IP addresses. So large number of internal addresses that still give you access to a small set using a small set of global external addresses. So for this we use an NAT router. Any address, any request that goes outside to the internet is routed using this router, and any local IP address is then replaced by the global address, and then the return packet will also return to this browser, return to this router, which will then replace the return IP, the local IP, local host. Now, how do we know which packet to return to which host? So the NAT router does this using a translation table. It keeps track of what request is from what IP. So this is just a small example. This is a private IP, and this is the external IP. So while going outside, it will replace this file with this. And while the return packet comes in, to replace this once more with this. Now, ISPs use NAT to conserve addresses. It allows them to serve thousands of customers using just hundreds of IP. You don't need to grant each connection its own unique IP. Now, we've gone over a lot of short-term solutions for address depletions. We've seen classless addressing, we've seen NAT. Another one is dynamic host configuration. Each host is given an IP address dynamically. But despite all these, address depletion still continues to be a problem, simply because there are too many hosts now. This, along with accommodation for newer features like real-time audio, encryption, authentication, have been the motivation for IPv6, the modern counterpart for IPv4. Now, this is 128 bits long, and the IP is divided into 16 bytes. They're represented as hexadecimal separated by 4 bits.